Dear friends, students and learners, welcome to the session on the design part of this material science course, and I have taken one part of this earlier in the previous session. So now we will be discussing about the part 2, and it will consist of some other design criteria. I am Shashank Srivastava from School of Engineering and Technology in the Gandhi National Open University. So earlier we talked about the Griffith and the Irwin criteria, but we haven't taken into account the plastic deformation around any crack tip. There was a crack tip for a certain body, so around that we hadn't taken the plastic deformation into account. So this both Griffith and Irwin criteria of fracture are actually applicable to materials that are brittle and have high yield strength, and we can note that the stress tends to be infinite as crack tip is approached. So as you will move near to the crack tip, meaning the portion of the crack, the upper portion of the crack, very near to that, if we move to that place, then the stress will be very large. You can say infinite. For R is equal to 0, the stresses are infinite at crack tip, meaning that the radius of curvature of that crack, if it is 0, then the stresses will be infinite, because then you know that area of cross section is almost 0, and whatever stress is there is in the denominator, the area comes, so that will become infinite. It however can be realized that no real material can bear infinite stress at any point, and hence this mathematical tendency to infinity cannot exist in any real material. So what we have talked about now, this infinity thing about that crack tip, actually it is not at all practical, it is an ideal thing. So it is just taken for the purpose of mathematical analysis. Otherwise in practical application it is not there. No such body is there where we will have infinite stress. What actually happens is that the material in close vicinity of crack deforms plastically, like you have read or learnt in the previous sessions about the plastic phenomena, meaning beyond the yield point, up to the elastic limit, up to the yield point, the material can come back to its original position after deformation, but after the yield point it becomes plastic, meaning it cannot come back to its original position, and it will retain certain amount of deformation. So that plasticity I am reminding you again here. So that's what happens, and so there is no infinite stress. Thus in all the engineering materials, a crack tip is always surrounded by plastically deformed zone of small size. So there is a very small zone of plasticity around the crack tip. The best size of the plastic zone can be calculated in one situation when material is regarded as non-strain hardening. Because if it is strain hardened, then its yield strength will increase, and then there will be no plasticity, instead brittleness will come in. So this strain hardening condition, non-strain hardening condition should be there. Hence the stress in crack tip plastic zone will not exceed the yield strength. So here are two figures, we will try to understand these. In the figure A, that is the first one, there is the sigma y yield strength, and it is marked on the y-axis, sigma y-axis, and the abscissa or the x-axis, there is the point of intersection of horizontal line at sigma y with the sigma yy r curve. So there is a curve in that. If you see the first figure, this is called the sigma yy versus the r curve, meaning the radius of the curvature of the crack tip is on the x-axis. So this curve is going down, you can see somewhat exponentially, and this if we draw a horizontal line from the yield strength point, then it will intersect this curve at some point, and from there we can draw a vertical line which will cut this x-axis at a certain point. This will give us this much length where it has cut will give us the length of our plastic zone. So that's what is shown in this figure, and in the figure B it is shown in hashed form. So that hashed form is the plastic zone of the material near the crack tip. So how does this fatigue crack propagation take place? Its mechanism now I will discuss with you. So if you recall, then in the section of fatigue, it was pointed out that the fatigue fracture surface has characteristics appearance marked by conchoidal lines. There we had discussed about conchoidal lines, if you remember. So these lines are also known as the striations, and these arrest the crack from moving forward, and the distance between two consecutive striations is the crack extension during one load cycle. So how much crack has grown is known through these striations. This has been confirmed by our replica fractography, this is a method, and also by electron microscopy. And in case of very strong alloys, they come very close to definition of brittle material. So very strong alloys, the plasticity is less and they are somewhat brittle only. So again here the mechanism we discussed. The first figure is A, if you can see. So it shows a crack in which the plastic deformation surrounds the crack tip. You can see the crack tip towards the left hand side of the figure A. So at A, crack is under compression or zero load. So no load is acting on this in the initial situation. The two faces are parallel, as you can see in the figure, or in contact, but the tip does not contact perfectly. And why it is so? Because of the plastic strains which have not completely recovered. So that's why it has not completely closed. They are separate at the tip, if you can see in the left hand side. When crack faces are pulled apart, like in the figure B, if you see, under the effect of tensile stress. So tensile stress is acting there, and it is acting at an angle of 45 degrees. See the arrows in the figure number B. So it is acting at 45 degrees, the tensile stress, and it helps activate slip along 45 degrees. So now there is slipping inside the material at an angle of 45 degrees. And this blunted crack tip actually extends in tip formation. So now you can see it has become larger in size, the tip. The displacement at crack tip increases to accommodate the plastic deformation. Then further increase in tensile stress will be there, and it will broaden the slip zone and reduces the stress concentration effect of the tip. So at the tip, which we had seen in the figure B, the stress concentration will now be less with increase in tensile stress. This effectively results in blunting of the crack tip into a semicircle ahead of previous crack tip. So it is somewhat like a semicircle. And in subsequent stress reversal, when we are removing the tensile force or load which was acting before this, if we remove it, then what will happen? The faces of the cracks are brought closer, but the semicircle created in figure C, if you see, it does not close sharply in a square end. So there is no square end, and it is not closing that sharply when the stress has been reversed. The end carried 245 degree lips, as you can see in the figure. Why? Because the slip zones does not recover as much as the central circular arc. So in the right hand side you can see the central circular arc. So accordingly this tip side has not recovered. So in figure D also you can see that thing, that this tip has not completely recovered. Thus an additional step is created along the crack length. So you can see in the figure D, there is an additional step that is given by delta A, which has come in the figure. And this crack begins to open again in figure E. And if you can see the figure E, as the tensile stress begins to apply on crack faces again. So if we are applying it again, then crack again begins to become larger, the tip tends to become larger. So in the figure D, you can see in this figure that increase in crack length, which is given as delta A, it very much depends upon the fact as how much stress is applied upon the two faces, the parallel faces, if you can see in the figure, and it is compressive type, and how much it is applied to bring them closer. So suppose this compressive stress is very small or zero, or even it is tensile, then the crack tip will not blunt perfectly even if two crack faces come closer, and it will have the semicircular tip intact. So that will be the case if the compressive stress is small or zero. and then it will require a few more cycles of this loading, meaning loading and then load reversal, for creation of 45-degree lifts at the crack tip. Apparently, the higher fatigue strength in pulsating or fluctuating stress cycle is explained by this phenomenon. So fatigue type of loading and fatigue strength is being explained here by this phenomenon. In high strength materials, it will be cleavage type of fracture that will occur at 45-degree angle approximately. So in high strength materials, we have a fracture called the cleavage fracture. And why it happens so? Because the slip zone will not be able to spread to the center of the crack tip displacement, because it is of higher strength. So the slipping that is taking place between the layers will not reach to the center of the crack tip actually. So this is about the brittle fracture. Now these figures you can see, when a tensile stress begins to work, one of the two cleavage cracks only will extend while the other will appear as striation. You can see in the figure here. See, only one of the two cleavage cracks is extending, the other one will remain as such. Now the effect of the plastic deformation on fatigue crack growth rate. We will discuss this thing now. How this plastic deformation will affect our crack growth rate in case of fatigue. So because of plastic deformation, the crack may close at a stress which is known as sigma CL, which may be higher than this sigma minimum, and this will effectively reduce the magnitude of delta Ki. All these things we have discussed in the previous session. Delta Ki is here, that is the stress intensity factor we discussed, so we are discussing again here. So effective value of differential stress intensity factor then can be written as delta K max minus delta Ki CL. So it will not be K min here, instead it will be Ki CL. So this delta Ki effective has now reduced, and Ki CL is given as sigma CL into Y into root A. So if you recall, it is the same formula, only the stresses have changed. So delta K effective then can be written as Y into a root of A into sigma max minus sigma CCL. So then there will be change, and the ratio of delta K effective to the original delta Ki will be equal to 0.4 R plus 0.5, where capital R is equal to sigma min upon sigma max. So fatigue crack growth rate is reduced in fluctuating and pulsating stress cycle. So from this formula we can see this thing, because what happens that the crack closes at a stress level which is higher than our minimum stress. So that's why then our effective K changes. Then there will be modification in Griffith theory also. Griffith demonstrated on certain glass specimens which were etched with hydrofluoric acid the validity of the expression which was worked out by him. But then one more scientist, Orowan, found that the Griffith theory in its original form could not be applied to brittle fracture of metals. Why? Because they have inherent capability to deform plastically. Thus for metals, Orowan introduced a plastic work term P, which represented the amount of work required to extend crack in the plastic zone. So that means we were earlier taking it to, the material to be completely brittle, but here even in this case brittle fracture, some amount of plasticity is there. So that's why Orowan took that plastic work term as P, and Griffith hadn't taken that, so there will be a modification. So hence the fracture stress for causing the crack to become unstable at metals will be expressed as sigma F, which is representing fracture, is equal to 2 into E into bracket open gamma plus P bracket close whole divided by pi into A and whole square root of this particular term. So you can see here that there is the extra term, that is P, is coming. The formula is same as the earlier. If you remember, earlier formula was 2E into gamma divided by pi A root of that. So if we see, then gamma is much lesser than P actually. So then we can neglect it. So the formula, new formula becomes as 2EP divided by pi A whole root. So here the ratio P by gamma has been found to vary between 100 to 500. So this P is much larger than gamma. That's why we are able to neglect that. And some experiments have shown that P decreases with decreasing temperature. So as soon as we decrease the temperature, then P decreases. It is quite obvious also that with decreasing temperature, brittleness comes in. So plasticity decreases. So this plasticity representing term P will also decrease. Erwin then replaced 2P by yet another term, that is GC, which is called crack extension force or the strain energy release rate, and its unit is given in joule per millimeter square or joule per meter square. So Erwin did another modification. Thus he got what new formula? Then sigma F is equal to E into GC divided by pi a whole root. So you can see that root 2P term that was coming has been replaced by GC. So now KIC will become sigma F into Y into root A, which is the previous term, and GIC will be then equal to KIC square by E. Here GC has been replaced by GIC, which is read as G1C actually, to properly refer to the mode 1. That is mode 1 we have studied in the previous session, how the fracture takes place. There were 3 modes, mode 1 and 2 and 3. So G1C and K1C are both experimentally determined, and other terms used to express GC are toughness or resistance force. So this GC actually is representing the toughness or resistance force. So now we can compare the Griffith theory. So the Griffith theory can be applied to continuous elastic fracture, and such a fracture is possible when material is inherently brittle. That is, the yield strength is higher than the cohesive strength or stress required to break the atomic bonds. And the next condition for such a fracture is that temperature is low or the crack velocity is high. So these were the 3 conditions for such a fracture to take place. Now we discuss about the cleavage fracture. So there are certain conditions that permit the stress, that is sigma yy, to build up to value equal to E. E meaning the Young's modulus, and thus initiate the process of breaking the atomic bonds. So this type of fracture due to the breaking of the atomic bonds is also known as the cleavage fracture. So whenever the sigma y tries to equal to E, then this type of atomic bond breaking takes place, and we term it as cleavage fracture. Instead of this, if the stress sigma yy at crack tip will not increase to E, then what we can say? We can know that material is then inherently tougher and the temperature is high and the crack has been stopped before this atomic bond breakage, and there is no cleavage fracture. Plastic deformation will occur in the region of crack tip, and that would not extend elastically. Griffith criteria of fracture stress will not be applicable in such a case. Under this condition, then Orovon's modified criteria will be applicable. When this will be applicable? Whenever that sigma y is not reaching up to value E. So cleavage and shear fracture at atomistic level. Now we can see at atomistic level, fracture occurs over regions whose dimensions are quarter of a micron. So you can consider that micron is around 10 to the power of -6 meter. So for a very small region we are taking. Fracture occurs at microscopic level over regions whose dimensions are of the order slightly in excess of 100th of a mm. So microscopic level type of fractures are like these, 100th of a mm. At atomic level, fracture occurs when bonds between them break across fracture plane and new surfaces are created. And this can happen by breaking of bond perpendicular to plane of fracture, and that is called the shear, and bond break by shearing of bonds across the fracture plane is known as the shear. So the cleavage occurs when local stress at atomistic level becomes equal to theoretical cohesive strength, which is E by 10. So the cohesive strength is around E by 10, and if this local stress reaches to this value, then cleavage fracture starts taking place. The theoretical shear strength is actually G by 10. Here G is coming because shear modulus we are talking about now, not the Young's modulus. And local shearing stress assumes this value to cause shear fracture. So here in the figure you can see both cleavage type of breakage of bond is there and shear type is also there. The top one is about the cleavage type. The vertical loading you can see is there, meaning in the vertical plane the load is there, tensile type, so cleavage is taking place. And in the shear type you can see the load is horizontal type and there is slipping. So now we take the case of fracture under uniaxial loading. The cleavage fracture beginning from any region of high stress concentration under uniaxial tensile loading will travel perpendicular to the tensile axis. So suppose the axis, tensile axis is like this, then your cleavage fracture will be moving in this direction, perpendicular to it. The profile of fracture plane of cleavage fracture will appear flat or square to the axis. So it will, from the outside it will appear as flat or square. All crystalline materials have preferred cleavage planes in each grain or crystal. Most metallic materials are crystalline that we know, and in their grains the cleavage planes may not be aligned perpendicular to the tensile axis. So it may not always be like this. So there may be a certain angle. And this will cause fracture plane to change direction, as you can see in the figure here. However, such change of direction will be confined only at microscopic level, and at macro level the surface will still appear flat. So this change of this plane actually will not be visible from outside, and when you view from outside it will still appear flat type. Like cleavage planes, the crystals also have shear planes on which shear fracture can occur. So both types of planes are there, cleavage as well as shear. In two adjacent crystals, the orientation of cleavage and shear planes may be such that one permits cleavage whereas other supports shear. So there may be two planes and one may be permitting cleavage, other may be permitting shear. Hence the crack at microscopic level may have a mixed mode. The gross appearance of fracture surface will be governed by predominant micro cracking. So here you can see in the figure the cleavage fracture and the shear both are shown in this figure. So depending upon which is more predominant, accordingly the shape of the crack will be formed. So we talk about the shear fracture now in the pure sense. Extremely localized plastic deformation actually causes shear fracture. So in a very small region plastic deformation is there, then it will cause shear fracture. And slip planes on which slip or sliding can take place exist in the crystals or grains of all crystalline materials, whether it be BCC type of metal or FCC type of metal. So suppose this is the specimen, and these are certain layers, if you can see in the figure, of the particular specimen. Different layers are there, and if shear is taking place, slipping takes place, and if only the middle planes of this particular specimen slip. Suppose here if you can see, this is one small plane up to this level and the other one is up to this level. So if these two are slipping only, then the crack which will be there will be slanting type, because the upper portion is not moving completely. Whereas if the whole body slips, then what you can see here is that this will be completely perpendicular, vertical type. So the crack will not be slanting in that case. So as shown, a slant fracture results when slip is confined to only one set of parallel planes. So such kind of fractures often occur in single crystals along planes at 45 degree to tensile stress. So examples of this is like the hexagonal close packing metals. At microscopic level, the fracture propagates along 45 degree to tensile stress, like given in this figure. In polycrystalline material, the advancing shear crack follows the path of maximum shear stress. However, it may be pointed out that this path depends upon the orientation of the slip plane and slip direction in a grain, so they may change also. Voids are formed at different points at inclusion, mainly non-metallic type. And when increasing deformation, these voids coalesce, meaning they come together to extend the crack. The formation of voids, suppose in a round specimen we take, when it takes place in the center. Why? Because enough plastic deformation has already taken place due to shear stress and resulted in necking of the specimen. So shear stress deformation, plastic deformation has happened to quite a large extent. So there's a necking tendency, and that's why the voids are there in the center. Then there will be reduction of diameter in localized region of specimen, like we have studied in case of the stress strain diagram also. So then these voids will coalesce, or the microscopic fracture path will become then perpendicular to tensile stress in tension specimen. So if this is the tensile stress path, then it will be, this voids will coalesce like this. On the microscopic scale, the fracture is quite jagged as the crack advances by shear mechanism. So it is not uniform type, and this fracture is often termed fibrous because of the fibrous appearance, and is shown here in the figure also. Final fracture in ductile materials like the low carbon steels takes place fast due to shear stress along 45-degree plane, if you can see in the figure, and this fracture is not jagged but smooth and wholly due to the shear. Now after discussing the mechanism of this shear and the cleavage type of fracture, now we move on to the factors that will affect the fracture. And earlier also we have seen this thing in case of the ductile to brittle transition. Here also there are certain factors. What are they? Similar to that: loading conditions, the temperature, and the stress and its concentration. So a notch actually produces triaxial state of stress, which tend to increase the yield strength. So if there is a notch, then yield strength will try to increase, making it somewhat more brittle type. So tendency of fracture will be more. The strain rate also increases the yield strength, so again tendency of fracture will be more brittle type of fracture. With decreasing temperature, there is ductile to brittle transition in both face-centered cubic and body-centered cubic metals. And this transition, the difference is that the transition is continuous in FCC, whereas it is sudden in case of BCC. The existence of a transition temperature is because the resistances to shear and cleavage behave differently with temperature. So this transition temperature, that is meaning from ductile to brittle, why it is there? Because the resistance to these type of fractures are different in case of the shear type and the cleavage type, and they behave differently with temperature. Ductility will depend upon the relative values of these two resistances. There are two kinds of resistances: shear and cleavage fracture resistance. Flow stress is reached before the fracture stress above transition temperature, but below the transition temperature the fracture stress is reached first. So this is the condition which is happening. So above the transition temperature, what happens? That flow stress is reaching first, so fracture will not take place. But below the transition temperature, fracture stress is reaching first, so fracture will take place and there will be no plastic effect. So it will be more clear from this figure that is given here. A notched specimen has a plastic constraint and hence shows a higher yield strength, as can be seen in the figure. If you see the figure, the strength versus the temperature curve, so there are two curves, and first one is, the upper one is named as the notched one. So notched one has a higher yield strength, that's why it is at the upper portion. The fracture strength or the cleavage strength, which is given as sigma f and will be represented on the y-axis by the dotted line, where the dotted line cuts the y-axis. It is least affected by temperature, and it is very much clearly given here in the figure, and as the temperature is increasing, it almost remains constant. The transition temperature occurs at the intersection of flow and yield curves. This transition meaning ductile to brittle transition, and it will be happening where the flow curve that is represented by the dotted line is intersecting the yield strength curve. So there are two yield strength curves, one is notched one and the other without the notch. The notched one is the higher. In the presence of notch, it occurs at a higher temperature, as you can see in the figure. At the right side, it is cutting the dotted line, whereas the without notch one is cutting at a much lower value of temperature. So the higher one, actually it is cutting at a temperature which can be very close to the room temperature. So then this transition, if it is happening at room temperature, it really becomes a big problem. And there are certain recent studies that have shown that at higher strain rates, the ductility transition shifts towards the room temperature faster than in case of the notch. So even worse condition is that of the higher strain rate, even worse than the notch. Notch has already got a higher yield strength, but if there is a higher strain rate, meaning yield strength is further increasing, then the condition becomes worse, and the ductile to brittle transition takes place very much near to the room temperature and can be really harmful. So in this session we discussed about the crack and the crack tip and how plasticity affects it, and the various types of fractures like the cleavage fracture and the shear fracture, and how they are affected, and what are the factors that are affecting the fracture, like the low temperature and the stress concentration or strain rate. All these things we have discussed in this session, and this finishes your unit number 6 of your course, and further the last unit will become, which will be on wear, unit number 7, and this unit 6 has been covered in 2 modules. Thank you very much.